All right, thanks. So it's a great pleasure today to have Professor Shields from University of Irvine. Omawa Shields basically works on exoplanet habitability and climate, and working mostly on this modern science of trying to bridge what we know of our own Earth and the climate on our own Earth into what might make an habitable planet outside. So it's a bit of a very interesting interdisciplinary area, which is actually quite interesting also for us here in Bologna, between the fields of exoplanets and the science of climate that we have at the university. Professor Shields has a very interesting career from my side, because she's one of us who decided to take a break for personal reason at some time. She, as I understand, she was fascinated by science and exoplanets and the space since a very young age, as most of us, I would suppose. But then she decided to take her own time to follow her own things, and then came back very successfully after a break of 11 years, if I'm not mistaken, into master PhD and then professorship in the US. I don't want to spend too much time. I just thank you, Awama, for being here today, and please, the floor is yours.
Thank you.
Is that
the yes.
There's axes up there. Yeah.
And this one here? Okay.
Okay.
All right. That way. Buongiorno a tutti. Sono molto contenta di essere qui con voi. È un grande onore per me poter dare una conferenza all'Università di Bologna. Mi piacerebbe parlare in italiano, questa bella lingua che sto studiando, ma penso che ci vorrebbero 3 ore di più. Allora parlo in inglese adesso. So before I leap into all the ways that my team is exploring the potential habitability of planets beyond the solar system, I want to cover what I consider to be the most important part of this talk. If you remember nothing else, please remember how to pronounce my name. So it's pronounced Aomawa. The emphasis is on the O. I thought for an interactive part of the talk, we could all say my name together. So on the count of 3, 1, 2, 3. Aomawa. Thank you. Grazie mille. And I'm also going to do something else that's probably a bit non-traditional, at least back home where I've come from, it is, and I'm imagining maybe here as well. And that's inviting you all to participate in a few moments of secular mindfulness-based practice. So this helps all of us sort of get on the same page, be in the same space together, leave outside of the room whatever came before and whatever is to come after. So it's not required, but for those who'd like to, I invite you at this time to close your eyes or keep them partially closed if you're more comfortable in this public space with that. And let's take a single shared breath together. And we can prepare for that by emptying all the air out of our lungs on an exhale. And taking a full deep breath, inhale in through the nose. And then sigh it out through the mouth. And then allow the breath to return to its natural rhythm. And notice for a moment where your body is making contact with the surface that's supporting you, the chair, the floor. And tune into the nature of that contact, the textures of the surfaces. Notice all the sounds you can hear outside of the room. Inside of the room. You might even be able to hear your own heartbeats at this moment. And notice how your body is feeling right now. Whether energized or tired, or a range of different sensations. And what, if anything, your body needs, whether rest or food. So notice what arises. And whatever arises, meet it with curiosity and interest, and without judgment. And acknowledge it. And honor the message, trusting that the needs will be addressed at the appropriate time. Let's take one more full deep breath in through the nose, sigh it out through the mouth. You can gently wiggle fingers and toes. And when you're ready, you can open your eyes. So our planet orbits one single middle-aged star in a galaxy of hundreds of billions of stars, in a universe of hundreds of billions of galaxies. So we are far and away from the first discovery of the first planetary mass companion orbiting another main sequence star like the Sun in 1995, a discovery that 6 years ago was awarded the Nobel Prize. We now know of nearly 6,000 planets orbiting stars beyond the Sun, and we call these planets extrasolar planets, or exoplanets for short, and we have them across a range of different regimes. And this number is only going to increase due to missions like the Transiting Exoplanet Survey Satellite TESS, which is the successor to Kepler. And unlike Kepler, which stared at one patch of sky for nearly 10 years, TESS is an all-sky survey. And so we're going to be discovering many more planets in the coming years. And many of these planets will be able to be followed up on with James Webb. And we've even already seen some characterization happening of Earth-sized planets with JWST. These space-based missions, along with ground-based large telescopes and platforms, are leading the way to what we hope will be a large-scale space mission like the Habitable Worlds Observatory, which will hopefully not just identify planets, but actually go into the deep work of characterizing these planets, looking for signs of life in their atmospheres. And of course, for observers, the end goal is to turn what is currently an artist impression, such as this, of an exoplanetary environment, this one as well, artist's concept of what an exoplanet landscape could look like, into an actual photograph, like this is, of the Tetons in Snake River, taken in 1942 by Ansel Adams. So again, trying to turn this artist concept into photograph. As we keep discovering more and more planets, there's a need to be able to not just identify them, but prioritize planets to look at for mission follow-up. We aren't going to have infinite telescope time to follow up on each and every potentially habitable world to look for signs of life in its atmosphere. Where once this was the only planet that we believed could ever support life, and this is a picture taken by the Apollo 17 mission, which was the last human mission to the moon in 1972, we now have dozens of potentially habitable worlds to choose from. And that number, again, is only going to increase. And so there's a need for a way that's combined, a two-tiered approach, using observational data where it's available, and also pairing it with computer modeling to fill in the gaps between what we do know observationally and what we must know to be able to accurately predict and characterize the habitability potential of these planets. So what my team uses are what's called global climate models, 3D global climate models, or GCMs for short. And these are the same climate models that have been used to predict climate and weather patterns on the Earth. They're the same models that were used to highlight and predict the future of carbon dioxide-induced climate change into the 2100s. But what we can do and have been doing is changing various parameters about these models to be able to predict climate and weather patterns on exoplanets. So GCMs solve the basic Eulerian equations of motion, which are shown here. And in doing so, they make two key assumptions. The first is that the changes in vertical density in the continuity equation and in the frictional force term of the momentum equation are negligible. And this is called the quasi-Boussinesq approximation. And what this does is filter out sound waves in the atmosphere, which change on very small, much smaller time scales, as in seconds, compared to the typical time step in a GCM, which is about 15 minutes. The second approximation that's made is that the horizontal scale of motion is much smaller than, much larger than the vertical scale of motion. And this is a reasonable approximation given that we're talking about planets, and the height of the fluid layer, in this case an atmosphere, is much smaller than the radius of the Earth, for example. So what that allows us to do is to neglect to first order changes in gravitational acceleration with the vertical height z. And we can approximate the momentum equation as the equation of hydrostatic balance. That's dp dz, change in vertical pressure, is equal to minus rho g, the density times the gravity. Okay, so now we know how the GCMs are solving these equations, how they are simulating the climate. Now we can move on to direct applications of the GCMs. So usually when observers find a planet, they're looking for planets that orbit their stars a particular region around the star in space. And that's denoted as by the habitable zone. That's this blue swath of space here, the region around a star where a planet with an Earth-like atmosphere could be expected to sustain liquid water on its surface. Too close in to the star and the planet is in danger of losing its entire water inventory to space in what's called a runaway greenhouse state. Too far away and the maximum CO2 greenhouse limit is reached. That's the point beyond which any further increase in carbon dioxide due to the presence of a carbon and silicate cycle, which operates on our planet to, by and large, in its natural state to regulate the silicate weathering rate with temperature, would no longer be sufficient to keep temperatures above freezing, and the oceans would freeze. But if only it were this simple. So in reality, the presence of long-term liquid water on a planet's surface is influenced by many more factors than orbital distance. And in fact, it's a bit overwhelming to think about, and it took several years for many of us in exoplanet habitability to get clear on all the different factors that govern long-term surface liquid water on a planet. So one of the specific factors that has really interested me for a good long while, even going back to graduate school, is the presence and influence of the host star's spectrum. So the interaction between the spectrum, the spectral energy distribution from the star and a planet's atmosphere and surface, and how that interaction could influence climate and habitability. When I was in graduate school, I stumbled into a journal club talk on this particular paper. It has a very long title, but the title amounts to this ice albedo feedback effect being different depending on the type of light that is coming in from the star and hitting ice on a particular planet's surface. So we typically think of, so I had this moment of bingo, that's what I want to study. That's what I want to learn more about. And as a graduate student, you're often looking for that light bulb moment, something that's going to keep you interested for several years leading up to a PhD. The ice albedo feedback mechanism is a climate feedback on our planet. It's a positive feedback, which means more makes more. So typically we think of ice as a very bright thing, a very bright white thing. And the more light that ice reflects, the colder the planet gets, reflects more light, temperatures get colder, more ice grows, etc. Right? Positive feedback. But ice albedo has a spectral dependence. So the ice albedo feedback mechanism is going to be sensitive to the wavelength of light comes from the host star. Ice, pure water ice, loves to absorb longer, redder wavelength light and reflects shorter, bluer light. This is why this iceberg looks so blue. The longer wavelength light is reflected on its way through the ice, the light's way through the ice, and only the blue light makes it all the way to the bottom to get reflected back up to our eyes, and we see a blue iceberg. So put more quantitatively, in the same way that host star spectra, of course, have a wavelength dependence. So I'm showing you here the sun spectrum in yellow, cooler star than the sun, slightly cooler, the K dwarf in orange, slightly hotter in blue, the F dwarf, and much, much cooler than the sun or any of the others, the M dwarf, a mid M dwarf 80 Leo in red. So too do surface compositions. Their albedos have a wavelength dependence. So what I'm showing you now on the y-axis instead of radiance is albedo or reflectivity, which is the fraction of light that is reflected away from a surface. So if it's 1, then all the light that hits a surface is reflected back. If it's 0, all of it's absorbed. So what you're seeing here, and this is a function of wavelength in microns, we have the ice of various grain sizes ranging from the finest grained ice, which is snow, down to coarse grained blue marine ice. And both of those, I'll show you, are shown right here in this photo. So that beautiful blue marine ice, very large grains. So we see that blue color. We see the light going all the way to the bottom and only the blue light making it back up to our eyes. Whereas with the finest grained ice, snow, there's so much scattering happening that we just see white. So we've got snow, blue marine ice, and then we modeled intermediate spectra between those two end members. And then we've included an ocean spectrum, super flat across the spectrum and very absorptive, and then a representative land spectrum here. So if you put ice on a planet orbiting a star like the sun, that ice is going to reflect most of the light that hits it, because ice reflects strongly where the sun emits strongly, in the visible and in the near UV. But put that ice on a cooler, smaller red dwarf star, M dwarf star, that ice is going to absorb most of the light that hits it, because ice absorbs strongly where M stars emit strongly, in the near IR. So one of the earliest studies I carried out on this phenomenon was really looking at how this specific aspect of water, pure water ice, can influence a planet's ability to go into these full-scale global glaciations where the planet is covered in ice, very much like we believe the Earth was happened to the Earth about 600 and 800 million years ago. We have these so-called snowball Earth states, and there's pretty significant geomagnetic, paleomagnetic evidence to suggest that this occurred. What we found when we looked at specifically applying this phenomenon to M dwarf planets is that given the more absorptive ice on M dwarf planets, and given what's in the atmosphere, if we assume that M dwarf planets would have, Earth-like atmospheric gases, water vapor, CO2, both of which also strongly absorb in the near infrared and infrared. They're the strongest greenhouse gases on our planet. That combined absorption, both in the atmosphere and by water ice surfaces, results in M dwarf planets being harder to freeze over and easier to thaw if they do freeze over. And I'll say more about M dwarf planets in general, but in a nutshell, we found too that they tend to be warmer than planets orbiting hotter, brighter stars, which is a bit of a kind of strange thing at equivalent stellar flux distances. So that was exciting and really kind of set me on a path to explore many different surface compositions, knowing that planets may not necessarily be completely covered in ocean. There could be many other surfaces possible, certainly water, but also there could be a lot of salt in that water, like we see here on Earth. And that could generate what's called a salt albedo feedback that I'll talk more about in a moment. Of course, like on our planet, there's many different types of land surfaces. What kind of land surface that an exoplanet could have, given that land surfaces are also wavelength dependent, their albedos are wavelength dependent. We have been looking into that as well. So our take home point from all this exploration, which is continued, is that the surface matters. And often when we think about detection and characterization of exoplanets, the surface often gets kind of ignored because it would be difficult, people think, to, and it certainly is still, to disentangle what's on the surface, to tell what's on the surface, given that we're so far away from these planets. But what we found is that the surface composition is incredibly relevant to climate and habitability studies, and that further work must be put into disentangling the atmospheric composition from the surface composition if we want to truly understand how accurately, how habitable these planets might actually be. So getting back to salt albedo feedback. So it turns out that if you have very, very salty ice, you can have that salt precipitate as sodium chloride dihydrate, also called hydrohalite. And it can precipitate to the surface of the ocean, the water, and form a crust. And so what you're looking at here is a brine pocket. And it's both two images taken 15 minutes apart at minus 28.7 degrees Celsius. And on the left, you see the brine pocket is filled with fluid. On the right, taken 15 minutes later, that brine pocket has filled with small crystals of sodium chloride dihydrate, which end up blocking the light. So I'll show you now what the albedo spectrum of hydrohalite looks superimposed on the spectra that you've already seen. So again, albedo reflectivity on the y-axis is a function of a wavelength. And we have that same flat ocean spectrum as well as the pure water ice and snow spectra. But now look what happens. Hydrohalite does not get incredibly absorptive in the near IR. It actually becomes and continues to be quite reflective at those longer wavelengths. And so we had to explore that when it came to M dwarf planets and how that interaction between host star spectrum and hydrohalite surfaces could affect climate and habitability. We also wanted to find out just how relevant this could be for habitable zone M dwarf planets. Like hydrohalite forms at these low temperatures below minus 23 Celsius. So we were interested to see if this is even something to be concerned about when we're talking about habitable planets, potentially habitable planets. So again, this is the region that this difference is quite striking. So we carried out studies looking at kind of the control case where we don't put any kind of parameterization into the climate model for when temperatures get below minus 23 C. We didn't do anything. We just left it as put water, assume that regular pure water ice is there. And then we had a case where we did change the albedo parameterization. When temperatures reached below minus 23 C, we started to change that albedo. And when they reached even lower temperatures, like minus 33 Celsius, we put a fully formed crust there. And we evaluated for both M dwarf planets and G dwarf planets at what incoming stellar radiation, that's basically installation for short, so in percent of what Earth gets from the sun. So 100% of the modern solar constant is currently the amount of incoming stellar radiation that Earth receives from the sun. So these percentages are percentages of that. We wanted to see at what installation this starts to become relevant. So we looked at when there's a non-zero result for the hydrohalite parameterization minus the control case. And we see that at about 65% of the modern solar constant, this effect starts to become non-negligible. And 65% of the modern solar constant is well within the habitable zone for an M-dwarf. Now, we were assuming Earth-like rotation periods for those previous simulations, but given the close distances of M-dwarf habitable zone planets to their stars, it's likely that their rotation periods would be slowed down, even to the point of being synchronous, which is when the planet's day is equal to its year. It's got a perpetual day side and a perpetual night side. And that's what you're seeing here. We ran some cases of synchronously rotating M-dwarf planets. So you've got that hot day side, and this is the night side. And these GCM data, for those who may not have seen results like this, it's basically like you're unfolding a globe. And so we've got latitude on this axis, y-axis, longitude, and this is a 3D plot. So you're seeing surface temperature. And what we see is that dotted line is where the freezing point of liquid water. And this is for a synchronous planet receiving 90% of the modern solar constant. So just 10% less flux than what Earth gets from the sun. We end up seeing that even on the day side, temperatures low enough for hydrohalite to form are reached. So these planets are even more sensitive to hydrohalite forming if they're synchronous. And what that's telling us is that it's really important to incorporate parameterizations for the formation of hydrohalite into climate models, because if we don't, then we risk inaccurately predicting the habitability of these planets. I want to pause for questions on that work briefly, and of course you can ask questions at any time, but I'm going to move on to land. But any current clarification questions? Yes.
So you discuss about the albedo of the water and salty water. So what is the situation when water is mixed with something else, other products like human product, like CO2 and things like this? So how does it change the albedo? Like for example, the highs that we have in Greenland or things like this. So do we have some idea? So this the albedo and how is the impact to the global variation of climate?
Yes, thank you for that. So for those who online who may not have heard, the question was we're talking about albedo being affected by the presence of salt. So what other mixtures could be present in the water, and how could they affect both albedo and the overall climate and energy balance of planets? So we're working on this right now. So we've taken these small steps. First, pure water ice. But of course, right, no planet's going to have just pure water ice and nothing else in it. So we want to get more and more realistic and accurate understanding of what these planets could really be like. So this first step was looking at the presence of salts. My grad student right now is looking at bacteria. So this is a logical next step, because during snowball Earth, we know that photosynthetic life even survived snowball Earth. So it was there before and it was there after. And that's continues to be a bit of a conundrum. If the ice was a kilometer thick, how did photosynthetic life survive? But we're looking at this right now, and it looks like so far, and these are really preliminary, the paper hasn't even been submitted yet, but the presence of the kind of bacteria that she's exploring seem to depress the albedo versus compared to pure water ice. And then we're currently looking at how that affects the overall energy balance. But this would be something that I'd love to do more work in, because yes, when you have these so-called, I don't want to even call them impurities, but things that are mixed, whether it's algae, and we're looking at different types of algae and different types of bacteria, then you're going to have, right, just by eye, there's a reflectivity difference. And so we must incorporate this, and thinking about where we put it in a climate model is also going to be important, because putting it, for example, at the equator will have a radiative impact that's different from putting it at the poles, for example, given the atmospheric circulation, the meridional circulation, and how that is influenced. So it's an area of active research, but so far, just looking at algae and other forms of bacteria, it looks like we're seeing lower albedos compared to nothing in there. Yeah, thank you. Yes.
Trying to get precipitation. So in other words, if it's cold enough, you get water cycles, so the surface is rejuvenated, or is it just ancient surface of ice?
There is evaporation and precipitation in the climate model. So we start off with a specific prescribed amount of water vapor in the atmosphere, and then we allow natural evaporation and precipitation processes to govern the amount of water vapor. And we do see precipitation happening. In a recent paper that I'll talk about too, we see snow on the planet in certain parts, and so yeah, all of that is prescribed in the model. Yes.
Does the quantity of salt in the water needs to be exceptionally high to have this entire crust, say, covered in precipitated salt?
Yes, it doesn't need to be anything. Well, currently what we found is that we prescribed it similar to Earth, and we still saw that this could happen at the certain temperature. So we have not looked at varying that to see if there's any sort of time dependence, which could be interesting. And if that would happen, if the precipitation would happen faster or be more concentrated. But I worked with a glaciologist, Regina Carnes, who used a certain concentration of salinity that was similar to what we would imagine to have been on Earth at the time. We were thinking about this in the context of snowball Earth, because we could have actually had the hydrohalite precipitation happen then, but we used pretty normal salinity at the time, and we see this happening. Great questions. Okay, so land. Of course, we only have to look outside of our windows and see all the different forms of land that exist on our planet, and even in our own little communities, thinking about the range of different land surface compositions that could exist on exoplanets is an also equivalently daunting task. So we start with one sort of simple framework, and I showed you this land albedo spectrum here. This is more of like a clay kaolinite surface. So representative land spectrum, meaning that it's midway between an average spectrum, what we would imagine. There are much brighter land surfaces, there are much darker land surfaces. So we've done work with this specific land surface, and then we've also varied the land surface. But you can see here, interesting, at those near IR wavelengths, land becomes more reflective than snow, right? Very fascinating. So we applied this phenomenon, this specific study, to TRAPPIST-1, the 7-planet system around an ultra-cool M-dwarf. All 7 of these planets are Earth-sized, and about 3 to 4 of them are in the habitable zone, depending on who you ask. And here on the top is a similar plot to what I showed you before, except now we have the specific TRAPPIST-1 spectrum here as our M spectrum. So ultra cool, so it's a little bit skewed more to the longer wavelengths than the 80 Leo spectrum I showed you before. And on the y-axis now, we've got, again, albedo, but these are just land surfaces with a couple of ice surfaces for reference. So we've got a really, really bright land surface, calcite up here, iridisol, which is similar to that kaolinite spectrum here in blue. And we've got the dune sand here in the brownish, and then we've got granite, very absorptive in black. And what we found was when we applied a range of these different land surface albedos to few of the habitable zone TRAPPIST-1 planets, the habitable zone planets, we had different resulting climatic effects. And this shows us the power of climate modeling, because we can apply what we've learned to actual observed systems and really determine how habitable they might be for a bunch of different parameters that we can't yet constrain with observations, such as surface composition. So what we found was that TRAPPIST-1d was the most likely candidate for a habitable environment, assuming it has a low albedo surface, like that granite surface or some other kind of igneous rock. So here, again, that sort of unfolded globe plot here, latitude, longitude, and you see that these are synchronous. These planets are pretty close to their stars, so we assume synchronous rotation. So you have that perpetual day side, the warm, that eyeball pattern there. And we also see that what's on the surface also drives what's happening in the atmosphere, because we also notice the increased cross-equatorial heat transport and energy transport for the lower albedo surfaces. So more heat absorbed by the surface generates more energy that's transported across the equator for these planets. Okay, so switching gears a little bit. Oh, yeah.
This one, why is it asymmetric?
Yes, so there are winds going on here on these planets, and the rotation rates are fairly short on these planets, given that they're synchronous. So often when we have that, we see this stretched out scale of circulation in these cases. So that's largely what's driving this asymmetric pattern, where we've got some stretched out atmospheric scales here and a little bit of some jet band behavior.
The dictation is a year, right? Kind of slope of stellar year. And how long is that? That's
Let's see, what did we assume for? I think for if it's these habitable zone planets, I'd have to look it up. But I think it was somewhere between around for M dwarfs 15 to 30 days, and their year, that's their day is equal to that amount of length, and their year is that long as well in the synchronous case. And then I'm going to show you towards the end of the talk the ultra fast rotating synchronous planet. Other questions?
So since it has the orbit of the planets, if it's on the ecliptic or is like tilted with respect to the position of the sun.
One more time.
Yes, yeah, so I'm talking about the orbit of the planet with
Mhm.
respect to the star. So how the light ray impact the surface. So if the orbit is very tilted with respect to-
inclination.
Yeah, inclination.
So we
That's kind of-
yeah, that would. We assumed zero inclination for these planets. And we've only ever done that in the model, in the climate model. However, I've worked with n-body models for the planetary system Kepler-62, and we have varied inclination. The inclinations of the orbits at the time when Kepler-62f was a system 1,200 light years away, but at the time it was one of the most potentially habitable planets to be found by Kepler, and the inclinations were not constrained at all. So we could vary them in the n-body model. But in the climate model, I think we can vary orbital inclination. We can vary obliquity, eccentricity, the angle of the vernal equinox with respect to periastron, but not the inclination as of yet. Something else I wanted to say about.
I guess the obliquity, right? The obliquity should take care of the inclinations.
And that would be zero in these
Yeah,
cases.
because you apply that a lot.
Yes. Something I was going to say about oh yes, and just it's always the star on the synchronous planet. We've always got, in terms of the light hitting, it's always noon on this planet, right? It's always that angle of the zenith is not changing. Okay. So the way that planets achieve global energy balance has been calculated for the Earth. Global energy balance, which was already brought up today, is this sort of thinking about how planets budget the light that they get from their star. And this is often how I start talking to students about planetary climate, is what governs global energy balance? How do we know a planet is in what's called radiative equilibrium? And well, it has to be that the energy that's absorbed by that planet must equal the energy that's emitted by the planet. And if those two sides are not equal, there's going to be a change in surface temperature. And we see that happening on our planet. We're teetering out of energy balance, but in its pure form, energy absorbed by the Earth must equal energy emitted by the Earth for the planet to be in global energy balance. So with both climate modeling and satellite data, the energy budget of the Earth was calculated by Kevin Trenberth and collaborators many years ago. And these diagrams called Trenberth diagrams were created. And when we know, however, the amount of solar radiation that comes in from the sun, we know some of that is absorbed. We know exactly how much is absorbed by the atmosphere, reflected by the atmosphere, how much makes it through to the surface, absorbed, reflected, and so on. We too, in turn, know how much the Earth has to emit and how that emission is budgeted to go back and radiate to space to avoid heating up or cooling down. But no one had ever calculated Trenberth diagrams for exoplanets. So that's what we did. And we knew from these earlier principles of the water ice albedo being lower for in the near IR and atmospheric gases absorbing more strongly in the near IR, we knew that M dwarf planets tended to be warmer than planets orbiting G or F dwarf stars at equivalent stellar flux distances. So of course, that's farther out for the G and F dwarf planets orbiting from their stars than the M dwarfs. But if you account for all of that, the M dwarf planets, all other things being equal, are going to be warmer. And you see that here in this plot with global mean surface temperature as a function of installation. Here's us, basically the Earth getting 100% of the modern solar constant from the sun. And here's this dotted line is the global mean surface temperature of the Earth, 288 Kelvin, 15 degrees Celsius. So to reach that temperature, the M dwarf planet only needs 88% of the modern solar constant. So 12% less than flux from its star than Earth gets from the sun, and it reaches that same temperature. The F dwarf planet, being a hotter, brighter star, but getting much more visible and near UV radiation from its star, needs more flux to reach that temperature, 108% of the modern solar constant. So we knew those numbers, but we didn't know exactly how the energy was budgeted throughout the atmosphere of each planet and surface to reach those numbers, to account for those differences. So we calculated Trenberth diagrams for these three different planets. Put the planet around a G dwarf, here represented here by the yellow star, and by an F dwarf and an M dwarf. And quickly looking at these three numbers here, you see that the sun emits that amount of radiation, and then 19% absorbed, 27% reflected, like from what gets down to the surface, 10% reflected. So then I'm going to go to the F dwarf and just pick one of these squares and track it as I go between the F and the sun. So F dwarf, sun, F, sun. You see how much less is absorbed on the F dwarf planet and more is reflected, and how much more is reflected by the F dwarf planet's surface compared to the G dwarf. Okay, again, remember, the F dwarf planet's receiving a lot more visible and near UV radiation, and the atmospheric gases are not absorbing that, not nearly as much, as nearly a large degree compared to the G dwarf. Then we go down to the M dwarf. So again, pick a square, and I'll go back from the F to the M. You see how much more is absorbed, for example, on the M dwarf by its atmosphere. 20% more absorbed compared to the F dwarf. A lot less reflected as well. So we basically made these plots and extensive tables with doing every single thing that had been done in these Trenberth diagrams for the sun, but changing the host star. We got to see specifically how this energy is budgeted and how that budget affects the long-term global energy balance of the planet. So that was, again, a really powerful application of climate modeling. And then I want to finish with a couple of more recent and really fun, almost science fiction studies that we've done that I'm excited about. So bringing you back to the habitable zone plot, this plot that I'm sure gets shown at every single habitability talk. I thought a long time ago, okay, so a planet orbiting an M dwarf so close to its star, that rotation period is likely slowed down to the degree of the planet being synchronously rotating. Could it be possible that you could have, on a synchronously rotating planet, an uninhabitable day side because it's way too hot, an uninhabitable night side because it's freezing, and only habitable conditions along the dividing line between the two sides, what we call the terminator? And it turns out that it's possible. And we did this study a couple of years ago. So this would constitute partial habitability. Again, we're looking for a scenario. It turns out it's difficult to create a planet that's only habitable right there, right? So we have to have too hot over here, too cold over here, but only habitable there, right? As we say, we call that scenario terminator habitability. And my postdoc, Anna Lobo, did this study together with me, and we found that if the planet is totally covered in ocean, it's very hard. It's very hard to have a terminator habitable planet, because what happens is you end up having the whole planet heat up and basically explode, not explode, but it becomes the runaway greenhouse state. All the oceans boil away everywhere. Or you have night side cold trapping, where everything is frozen. The water gets night side cold trapped on the night side, and then temperatures are too cold on the day side too. So if we have aqua planets, it's unlikely that we would encounter this terminator habitable regime. They're either habitable in a lot of parts of the planet or uninhabitable everywhere. But if you have a water limited planet, aka a land planet, it's easier to do. And it turns out that we're able to create this scenario. Again, you have a little bit of water, but we can call this planet mostly desiccated, where it's almost akin to a dune-like world. And we're able to get more of this kind of demarcation between habitable temperatures, only uninhabitable on the day side, uninhabitable on the night side, but having this this nice strip along the terminator. There's less moisture transport happening on the land planets, right? There's less moisture in general. And so we can have these water limited regimes. And it turns out M dwarf planets could be water limited in general. They are born from a nascent nebula, which is much more limited in terms of its water availability. And so they're likely to be to have less water to begin with. They've also applied this study to the K-dwarf planets. K-dwarfs get often overlooked when it comes to habitability studies, but they carry a lot of advantages in that they don't necessarily have some of the concerns that M-dwarf stars do, not as active stellar activity, and yet they still have very long lifetimes for planetary and biological evolution. And it turns out that the K-dwarf, the habitability terminator situation can actually occur more easily on a K-dwarf environment, a K-dwarf planet, given that there's less opportunity for night side cold trapping on these planets. So I've provided the QR code for if you want to read more about the studies we've conducted on this topic. I also most recently looked into white dwarf planets. So as most of you know, white dwarfs are the end stage for most of the stars in our galaxy. Certainly our sun will become a white dwarf. And it's often been believed that by the time the star gets to a white dwarf, there's probably not going to be any planets around it because of the tumultuous stage and levels of processing that brought that white dwarf to its current stage. The red giant phase most likely engulfed in the inner planets Then you had the planetary nebulae, and then this white dwarf at the center, which has ceased to undergo nuclear fusion. So it's this dying ember in space. But gas giant planets have been found orbiting white dwarfs, and debris disks have been found orbiting white dwarfs. So it's possible that we could find Earth-sized planets in the future around white dwarfs. So we wanted to explore what would the climate of an Earth-sized planet around a white dwarf star look like compared to a similar planet orbiting a main sequence star. Again, this plot. So we compared a main sequence planet, so the planet's orbiting a K dwarf, a little cooler than the sun, and its habitable zone planet would orbit here in the nice blue swath. And then we chose a white dwarf star, similar effective temperature, but because this white dwarf is it's such low luminosity, cooling with time, its habitable zone is right there. Right? It is super close up to its star. So as a result, it's got a very fast rotation and orbital period. It is absolutely, would absolutely be synchronous. And we assumed, at least at first, synchronous rotation for both planets. So and the K dwarf star, the main sequence star we assumed was the star Kepler-62. So we used that. And this planet is sort of a hypothetical planet that could be orbiting 62e, between 62e and 62f. So here on the left side, that K dwarf planet has an orbital period of 155 days. And you see this classic eyeball pattern. This is surface temperature that I'm showing you. The white dwarf planet, look at it. It's got 0.44 days. That's 10 hours is its rotation and orbital period. So we call that ultra fast. And this pattern has been termed a bat rotator regime because of how it looks. And it's very interesting because you see these banded structures. The atmospheric scale is super stretched out. And we see warmer surface temperatures happening on this white dwarf planet. And in fact, we have these warmer nodes right in the mid latitudes. And this is, again, that 10-hour rotation compared to 155 days. We have extremely stretched out scales of atmospheric circulation and these jets, essentially. So we've got these warmer temperatures, and the reason for that is rotation period related. Then I'll show you also total cloud fraction. So same thing, K dwarf planet versus white dwarf planet. We've got a lot of clouds on the day side, which are reflecting a lot of radiation back out to space. So that's cooling the K dwarf planet significantly. And we don't have nearly as many clouds on the day side of the white dwarf. In fact, these clouds are stretched out and more homogeneous across the entire planet. And to show you the difference in cloud more strongly, we look at a 2D plot, total cloud liquid water path as a function of latitude. And the K dwarf planet's right here. Here's its day side, big cloud there on the day side, lots of cloud, and the white dwarf is here. So not having as much cloud on the white dwarf's day side allows it to retain a lot more heat compared to the K dwarf planet. And we see this also by looking at shortwave cloud forcing. So you can see a lot more cloud forcing happening on the K dwarf compared to the white dwarf. There's also something interesting happening on the night side. So shortwave cloud forcing here, but if we look at long wave cloud forcing is a proxy for the contribution to the night side greenhouse effect, or the greenhouse effect on the night side. So if we look at the night side here, over here, and over here on the white dwarf, we have these areas of fairly high long wave cloud forcing compared to a pretty low amount here on both, and homogeneous on the night side of the K dwarf. And what we can see when we dive more quantitatively into the data, we see that the K dwarf planet is emitting on average about 18 watts per meter squared to space on the night side, more than the white dwarf planet. Again, cooling it off much more significantly compared to the white dwarf planet. So it's always been believed that, having a heavy cloud layer on a synchronously rotating planet could be an advantage. And it certainly could if the planet is orbiting close to the inner edge where it's in danger of overheating. That cloud reflecting the heat, the energy back to space could be quite good, cooling the planet off and buffering it from a runaway greenhouse. But if your planet is smack in the middle of the habitable zone, this could be a downside, having too much cloud. And in fact, it does seem to reduce habitable surface area compared to the white dwarf, which has less cloud. So I was very excited to do this study with a class of planets that are often written off as not being very habitable. And it turns out they could present a number of possible good prospects for habitable zone real estate. And finally, my grad student has looked at, again, eccentricity. We were talking about changing the orbits of these planets because there's a lot of eccentricities beyond zero that exist within the exoplanet population. And this habitable zone in the green swath is always assumes circular orbits. The habitable zone plot I've shown you 3 times assumes circular orbits. And very little had been done looking at how habitable a planet could be as a function of its entire orbit. So throughout its orbit, one of my students about 5 years ago calculated the fractional habitability as a function of eccentricity and host star type. And now we've gone even further, looking at a different surface composition that could be expected to form on eccentric planets and distant planets. So it could be that temperatures get cold enough, of course, for water ice to form, for temperatures below the freezing point of liquid water, but also cold enough for CO2, perhaps, to freeze out of the atmosphere onto the surface. Right, that happens at about 194 degrees Kelvin at its 1 bar surface pressure. So my grad student has calculated how the radiative impact, because CO2 ice is quite reflective also at near IR wavelengths. It's very reflective, much more reflective than water ice. And so her work, which I'm happy to talk more about offline, is featured in this the cover of the journal Astrobiology, and made the cover of the journal Astrobiology, and is featured in this first inaugural issue this year. And her QR code is there to scan for more info. So the main takeaway point from what I've shared with you today is that this surface composition of exoplanets we found to be incredibly relevant and important to consider when we want to make accurate habitability assessments for these planets. And we're really entering a stage where we're moving beyond kind of idealized model situations to accurately and realistically predict what these surface compositions could be and how they could influence habitability. And as Leonardo mentioned, I have a bit of a non-traditional background in that I left astronomy for over a decade, and he was right, 11 years exactly, to pursue a career in acting. And then I came back to astronomy all those years later, and I chronicle that experience in a memoir that was published 2 years ago by Viking. And it hasn't yet been published in Italy, but I'm hopeful. It's been published in the UK and is about to be published in Korea. But you can probably acquire it in English here somewhere, and it's definitely on Amazon. And I'm also founder and director of an educational outreach program called Rising Star Girls, which encourages middle school girls, so that's ages 10 to 15, of all colors and backgrounds, to explore and discover the universe using the creative arts. So we conduct virtual workshops every summer. We want these girls to know that in the same way that if they only looked at the galaxy in one type of light, like the visible in this case, they'd miss out on so much compared to looking at it in the infrared as well. So too is there so much more to these girls than meets the eye. So if you'd like to learn more about Rising Star Girls, please visit our website. And we have our first peer-reviewed journal article that really chronicles the approach and the efficacy of our methods. And that's been really exciting. So you can learn more about that. And finalmente, I have been practicing a particular type of rest-based meditation for a few years now, and I've now been certified, and I've started to carry out these workshops at academic campuses The particular type of meditation is called Yoga Nidra, and I want to share a little bit about it. It's a sleep-based guided meditation that's carried out lying down, ideally, although you can practice it sitting up as well. And its benefits are significant. It's been shown to improve sleep quality and reduce anxiety. And it's been used in partnership in the States, in partnership with the Walter Reed Army Medical Center and the Department of Defense to treat soldiers with PTSD, and has positive outcomes among numerous populations, including college faculty. It's been said that 30 minutes of Yoga Nidra feels like 3 hours of sleep in the body, and I can attest to that being true. So I carried out workshops at Princeton University earlier this year and at Caltech last year. And this is a picture from the Caltech workshop. So, and I'm happy to give more information for anyone who might be interested. There's a lot of wonderful apps where you can listen to the meditations on your own as well. And this is a picture of my family. So I'll be I'm planning to apply for a Fulbright fellowship to come back to University of Bologna and teach exoplanet climate and hopefully teach some rest workshops too. And so if that works out, then hopefully some of you will meet them as well. We have a couple of pictures in here from Italy too, one in Florence and one in Arezzo. I think I always like to show pictures of myself and mention hobbies outside of work so that students know that they often believe that professors were born as fully three-dimensional, fully formed adults out of the womb. And so it's good for them to know that we have lives too. So the takeaway points. It is this two-tiered approach of using both observational data and computer modeling that will allow us to make the most accurate predictions of the habitability of exoplanets as they are discovered and as we hope to discover them. It's likely that M-dwarf planets are warmer than planets orbiting stars with more visible and near UV output at equivalent stellar flux distances. Surface composition is an extremely important factor governing planetary climate, and we must continue to explore it and work to constrain it observationally. And it turns out that planets orbiting white dwarf stars may be just as, if not more so, amenable to life compared to planets orbiting habitable zone, main sequence habitable zones and habitable zones. I want to acknowledge the University of Bologna for this opportunity to be here today, my host institution, as well as my home institution, and funding sources, and my collaborators. So thank you all for your attention.
So we stopped it with many questions during the talk, but please, if you have questions, Cheng.
It's amazing talks. It's a lot of it. I have a question in the curiosity maybe about the Terminator habitability.
Yeah.
So how about like using phase curves to look for some biosignatures for this habitability around surrounding Terminators? Yes. Since like we can actually catch up, like we can actually observe the Terminators using phase.
Yes,
Is it a good strategy?
It is a good strategy. So we're actually working on that next. So we've been looking at these using just the climate modeling. And even with climate modeling, you can make thermal phase curves and pull out that information. But what we're planning to do is do a dedicated paper where we use observational simulators, maybe James Webb or maybe the planetary spectrum generator, and really try to see at what phase we can see what for these Terminator planets. So that's in the works. Yeah.
Looking forward to it. And I have another question about the planet orbiting white dwarfs.
Yeah.
So it might be a stupid question. So why do we assume that the atmosphere still survives in these planets? Because I would assume that if you already have a white dwarf, the interstellar environment might be not really good to keep the atmosphere.
Yes. Yes. And you mean the planet?
Yes.
Yes. That's the opposite of a stupid question. I think there are no stupid questions, and that's a very, very good one. So for those online, the question of why can we even assume that the planet's atmosphere survives around a white dwarf, given the incredibly tumultuous stage and various stages leading up to the formation of the white dwarf. So it's a stretch to assume that the entire atmosphere survives. As we've seen, giant planets have been found around white dwarfs. Now, it could be, given that we found hot Jupiters and we're wondering, how did hot Jupiters form? They're right up against their stars. Currently, planetary migration is the prevailing theory, that they started farther out and then they migrated in. It's possible that same principle could apply for Earth-sized planets. Perhaps the distant, what would probably have been uninhabitable, way too cold planets, when they were prior to the white dwarf stage, ended up becoming that became the habitable zone real estate later on once they migrated in, because the rocky planets that were interior were engulfed. Now, we do run into some issues there with, if the planets were that far out, perhaps they were too far out to have kept an atmosphere, given we talked about CO2 ice that could have frozen out. But we're thinking about, and we're looking forward to exploring the CO2 ice question and with the GCM. This work that my grad student did was with an EBM. With a GCM, an EBM, is a one-dimensional energy balance model, and you can't do very much with atmospheric dynamics. So with the 3D model, is it possible that the atmosphere could freeze out and then sublimate back up into the atmosphere at periastron, when the planet's closer to its star and the temperatures are more clement? This is something that we would look into. So if we assume a planet was too far out at one point, and that it may have lost its atmosphere, perhaps it frozen out, it froze out onto the surface. Perhaps once this planet migrates in, because it's on an eccentric orbit, or because the white dwarf is now the white dwarf, and perhaps that atmosphere reappears and we have a habitable planet. But again, these are all conjectures, and you're right to question the mechanism that by which the atmosphere could sustain itself. But I think we've seen in many cases, at least on Earth, life finds a way, right? Life found a way during Snowball Earth. Even if there was a complete 1 kilometer thick ice, we know how much life there exists at the bottom of the ocean that doesn't need sunlight to survive. It uses chemosynthesis rather than photosynthesis. So it seems like wherever there's liquid water, there could be life. Thank you for those questions.
There are questions there in the room? Then I don't know whether on Zoom there are questions. I don't see. People should speak up if they want to ask questions, because I know.
Oh, the chat, yeah. Let me see.
Yeah. Okay, yeah.
Oh, yes, there is a question.
Oh, there is a question. So let's.
Do your albedo wavelengths consider weathering-induced albedo changes? Ooh, thank you for that question. Okay, yeah. Do your albedo calculations include weathering? So no, don't. But so weathering, this silicate weathering, I mentioned the carbonate silicate cycle. So on Earth, we have this wonderful negative feedback process that largely regulates the planet's climate with temperature. So if temperatures are too warm, we have a lot of precipitation that scrubs CO2 out of the atmosphere, locks it into rocks. And then the rocks get kind of washed down into the ocean, subducted under oceanic plates. Now, if temperatures get too cold, then we can remember there's volcanic outgassing that continues to happen, and the CO2 gets put back up into the atmosphere through volcanoes and warms temperatures. And that's this negative feedback, in that more creates less. So more temperatures will eventually create colder temperatures, and colder temperatures will create warmer temperatures. So it's been pretty much kept our temperature mostly in balance, in its natural form. Of course, now we are not able to, and then Snowball Earth most likely was a situation where we had so much continent at the equator that there was so much CO2 drawn out of the atmosphere faster that it could get put back up through volcanoes, and we had this globally ice covered surface. But by and large, it's kept temperatures pretty pretty consistent. So to think about weathering, right, that process of weathering, which is like bringing the, locking the CO2 into rocks and bringing it out of the atmosphere. When you do that, I think that it would be wonderful to include this in climate models, and most climate models are not dynamic in that way. You're simulating the planet's climate given a specific atmospheric composition, which you prescribe at the beginning of the model. Then you run the model till it reaches equilibrium. Now, if you want to change the atmosphere, you can do that. You can stop the model, or at the end of the simulation, you can change the atmospheric composition and run it again. But you can't, currently, we're not able to do it dynamically, where we change the albedo as less CO2 is in the atmosphere, for example, because that's going to change not the surface albedo, but the planet's albedo, because CO2 in the atmosphere is going to, if there's less CO2 in the atmosphere, there's less absorption happening by the atmosphere. So, for example, our planet's surface albedo might be, 0.4 or something, but when you include an atmosphere, the atmospheric absorption, its overall albedo of the whole planet, surface and atmosphere, is like 0.3. So yeah, that would be a great thing to do, to start to think about modifying climate models so that we could really see how the albedo changes as a weathering rate changes. Because what we do see is during the course of a simulation, we can see changes in albedo. But again, we're starting with a certain prescribed atmospheric composition. So it's not dynamically changing the atmosphere as weathering occurs, for example. So yeah, good point.
Alessandro had a question.
Okay, thank you for the wonderful talk. I just have a curiosity. So if since planets around them dwarf or a bit closer to the star, have you looked at, or do you think that the variability of the star itself, like flares, coronal mass ejection, or solar wind interaction with the magnetic sphere, will affect the climate of this planet? So,
Yes, it absolutely will. And we have not looked at stellar flare activity specifically. I did write a review paper on the habitability of M-dwarf planets a number of years ago, and we talked about the flare activity quite a lot in that review paper. But what I've seen is photochemical models that are used to explore flare activity, and it looks like it certainly could affect, for example, the presence of an ozone layer, having that increased flare activity, and M-dwarfs very well could have, for the first billion years, they live for hundreds of billions of years, so they have these really long pre-main sequence phases, and that first billion years, they could be pelting the planet with X-ray and UV radiation. It might be that life would only have a chance of surviving it if it was at the bottom of the ocean. So that's a way, but it does look like in photochemical models that the ozone, there's significant impact on the ozone layer of a simulated planet when you incorporate certain amounts of stellar activity. I think what people have found is if you don't include sort of the large, coronal mass ejections that can happen, then your ozone layer is not completely obliterated, but certainly would be impacted.
Thanks. Thank you very much. Thanks again for this beautiful. Of course, if some of you want to stay and have more discussion, we can have more discussion. But in the meantime, let's close the official room of the seminar. Thank you very much. Thanks a lot for this.
Thanks everybody online.
I'm just gonna stop the recording somehow.
Thank you. Bye-bye.
Bye.